Okay, welcome to the third installment of the video series on the periodic table. And this short video is going to address specifically the periodic trend called atomic size, all right, or atomic radius. We're interested in the size of different elements because the size of a particular element influences its physical properties and also its chemical properties. And so what we want to be able to do is utilize the periodic table in order to make qualitative comparisons about the size of different elements. So in order to do that, we need to understand how the various trends work. Now, when I talk about a trend, what I mean is the following. We're going to make these comparisons based on two different ways of thinking. We're either going to talk about how the size of particular elements change as we move down a group from the top to the bottom. So for example, we might want to know the size difference between hydrogen, for example, and cesium. And we're making this comparison in a specific group of elements, specifically group 1A. The second way that we're going to consider the trends on the periodic table is horizontally, moving across any particular group. Like, for example, we might want to know the difference in size between lithium and neon, both of which fall in period 2. All right, so what are the trends? We're going to start by considering the difference in atomic size as we move down any particular group. All right, so to talk about that, I'm going to focus on group 1A. And as we move down any particular group, the size actually increases. So as we go from hydrogen to cesium, these elements become increasingly bigger. Now, the reason for this should be pretty obvious. When we start with hydrogen, we're in period number 1, which means that for period number 1 elements, we're actually filling energy level 1 with electrons. When we move down to lithium, we see that we're in period number 2, which means that we've actually added another energy level to the element as we move down from hydrogen. And then by the same token, as we move down to sodium, we've added yet another energy level. We've gone from energy level 2 to energy level 3. To potassium, we're now in energy level 4 and 5 and so on as we move down a particular group. So another way of thinking about this is if we were to say, okay, well, hydrogen is the heart of an onion. And as we move down a particular group, as we go from hydrogen to lithium, what we've done is when we moved into energy level 2, is it's as if we've added another leaf of an onion. All right, and then from lithium to sodium, we've added another leaf. From sodium to potassium, another leaf. And as we do that, the radius or the diameter of the particular elements is rapidly increasing. So the reason why elements increase in size moving down a group is because we're adding successive energy levels, and this is making the elements as we move down a group thicker. All right. Now, as we move left to right across the periodic table, so say we start with lithium and we move across period number 2 from lithium to neon, we have a different thing that happens that is rather counterintuitive. So let me explain what the trend is, and then I will describe the reason why. So the trend is, as we go from lithium to beryllium and then eventually to neon, is that the elements are actually decreasing in size. They're actually getting smaller. The reason this is counterintuitive is that you can obviously see that the atomic number that we start with lithium is 3, and we're finishing with neon with an atomic number of 10. In addition to that, you can also see that mass is increasing. We start with lithium at 6.94 grams per mole, and we're finishing with neon, which is about 20. So if that's the case, if we have an increase in atomic number and the mass of the element is increasing, it seems to follow that the radius should actually be increasing as we go left to right across the table. So why is it actually directly the opposite of this? Why do the elements decrease in size as we go left to right? Well, the reason is twofold, all right? So let's start with the first part of this. As we go from lithium to beryllium, and then from beryllium to boron, and then from boron to carbon, we're adding protons. We go from boron to carbon, we've added a proton in the nucleus of the atom to become carbon. This has increased the number of positive charges that are in the nucleus. So we go from carbon to nitrogen, we go from 6 protons to 7 protons, so we've effectively added another positive charge in the nucleus. So what's happening is we move from left to right across the table. So for example, from boron to neon, is that we have systematically increased the magnitude of the positive charge which is in the nucleus of the atom that's responsible for attracting electrons. Now let's shift back over here to the left and talk about the electrons. Remember that we're making a direct comparison of elements, lithium all the way to neon, that are in period number 2. And by definition, period number 2 means that we are filling energy level 2 as we move from left to right across this period. So as we go from lithium to neon, we are filling energy level 2 with electrons. Now here's the trick. What you need to recognize about this is that as we fill energy level 2 with electrons, each subsequent electron, as it's being added to that energy level, is going into the same identical energy level and is the same exact distance away from the nucleus of the atom. So in boron, we have 5 positive charges in the nucleus, and we have 5 electrons. All 5 of those electrons are in energy level 2, and they are the same distance away from the nucleus. When we shift to carbon, we've added more positive charge in the nucleus, yet the additional electron is going into energy level 2 and is the same distance away from the nucleus as the electrons are in boron. So the bottom line is that as we move left to right, we increase the magnitude of the positive charge in the nucleus, which increases the power of attraction that nucleus has for electrons, yet each new electron that comes in is the same distance away, is the same distance from the nucleus as the previous electrons. Yet they are being attracted by a progressively higher and higher attractive force because we've increased the magnitude of the positive charge in the nucleus as we went from left to right across the table. So what happens is those electrons are being attracted with higher and higher amounts of electrostatic force, and the result is that there is a general compression of the diameter. Those electrons are sucked in, and we end up decreasing in size as we go left to right across the periodic table. So to reiterate, 2 trends. Atomic size, top to bottom, down any given group, atomic size increases. The atoms get bigger. Hydrogen is smaller than cesium. As we go left to right across the table, sodium, therefore, is larger than chlorine because the radius or the size of the atom decreases moving left to right.